Vanakkam. Welcome to this video on biomechanics. We have been looking at biomechanics of soft tissues. Specifically, in the previous videos, we have been looking at the mechanical properties of tendons. We looked at stress strain relations. We looked at the models of nonlinear elasticity within the physiological or the toe region. We continue our discussion on tendons and tendon behavior in this video. So, in this video we will be looking at gliding resistance, we will be looking at tendon wrapping, we will be looking at friction forces in tendons that wrap around the bone, okay, or forces in wraparound tendons. Those tendons that wrap around the bone we call as wraparound tendons. And using this methodology or using this approach or methodology, an experimental measurement of the friction between flexor digitorum profundus tendon and the A2 pulley of that tendon that has been measured. So, when there are movements that happen in a joint, tendons slide over some distances, and they have a need to overcome this gliding resistance. Tendons are usually surrounded by a covering or a sheath, some cover or some material that covers the tendon, a sheath, right. And the purpose of the sheath is to provide a low friction environment to provide nutrition. One of the ways the body keeps the friction low is by the use of synovial fluids. Some tendons do not have synovial fluids and they are called extrasynovial tendons. Okay. The tendons that have synovial fluids are called intrasynovial tendons. So, the resistance, so if tendons are going to slide and glide over this, the amount of resistance, the gliding resistance depends on many things. Of course, you would expect that this kind of friction will not have a contact area dependence, but that is not actually true. The relative size of the tendon and the surrounding sheath plays a role, and lubrication, the amount of lubrication, the quality of lubrication plays a role. So, gliding resistance depends on lubrication, relative size of the tendon and the surrounding sheath and such factors. Okay. In fingers, the friction coefficient between the flexor tendon and the A2 pulley was measured to be between 0.02 and 0.063. Okay. This is the friction between the flexor tendon and the A2 pulley. We will discuss this experiment and the paper later. Okay. We will discuss this experimental approach and the corresponding paper a little later. There is a need to reduce gliding resistance after surgery that is performed for tendon repair. So, after sports injuries or after any injury, if the tendon is ruptured and tendon repair surgery has been performed, there is a need to reduce the gliding resistance. This is achieved, usually this is achieved through proper suturing and the appropriate choice of biomaterial and the quality and the quantity of lubricants or lubrication that is available. What is shown here is the tendon. This is the tendon of the fingers, right. And these are the various pulleys through which the tendon glides over, through which the tendon traverses. These are called as the A1 pulley, A2 pulley, A3 pulley, A4 pulley and A5 pulley. Remember, this is the whole finger, this is the distal phalange, this is the dip joint, this is the middle phalange, this is the proximal interphalangeal joint, this is the proximal phalange, this is the metacarpophalangeal joint. Am I correct? Can you check this? You can check this with your understanding of anatomy that we discussed long time ago. In the beginning of the course, when we discussed the finger anatomy, hand and finger anatomy, we have discussed this in much greater detail. By just looking at the picture, I have described what is the distal phalange, what is the dip joint, what is the middle phalange, what is the pip joint, and what is the proximal phalange, what is the MCP joint. Remember, what is DP? Distal phalange. DAP is distal interphalangeal joint, PAP is proximal interphalangeal joint, MCP is metacarpophalangeal joint. Okay. The proximal phalange is called PP and the middle phalange is called MP. Just check this once. Okay. So, these are the 5 pulleys that are of interest for us. These are called as A1 pulley, A2 pulley, A3 pulley, A4 pulley and A5 pulley. The coefficient of friction between the tendon and that A2 pulley is the one that was measured using the experiment, that we will discuss later. Okay. This is that pulley that we are talking about. Now, tendons either directly connect to the bone or they wrap around the bone and then connect. So, those tendons that connect to the bone directly without wrapping around it are the direct tendons. Okay. Sometimes tendons wrap around a bone or wrap around a pulley and then connect. Okay. This wrapping around a pulley are called as, or those that wrap around the bone or wrap around the pulley are called as the wraparound tendons. Those that do not do that are called as the direct tendons. When curved tendons, when they exert a force, usually what they do is that they also produce a force towards the center of curvature. So, they are curved, and so when they produce a force, they tend to straighten a little bit because they also produce a force towards the center and they also straighten a little bit. When these kind of wraparound tendons slide, the friction felt by them is much greater than the friction felt by the direct tendons. Why is this the case? So, let us say there is a bone, a cylindrical structure, and a tendon wraps around, stays in contact and then goes out like this and goes out like this. The friction felt by this tendon is much greater than the friction that is felt by a straight direct tendon. Why is this the case? We will have to check why this is the case, because one likely reason is that the contact area increases, but you would say that the contact area does not affect simple principles like simple friction mechanisms such as Coulomb friction. But actually this is not true. In many cases, contact area tends to have a very important role in deciding the amount of friction and the amount of resistance. In terms of friction, maybe coefficient of friction might not change, but the amount of force that is felt will be affected by the contact area. Well, if that is the case, would that happen in a flat surface also is another question. Mostly this also happens in a flat surface, but the amount of friction, the amount of frictional force that will be felt in a wraparound or in materials that wrap around a cylinder, for example, in this case, is much greater. Why is this the case? We will have to see, and that is what we will be discussing in most of the remaining part of this class. Okay. Now, let us consider wraparound tendons that wrap around a cylindrical structure. By the way, remember we discussed this the case of the pulley and what is the purpose of this kind of pulleys and wrapping around. We discussed this. For example, one example that immediately comes to my mind is the case of the patella. Remember, the tendon from the quadriceps, right, wraps around the patella. Why is this? Because there is a need to increase the momentum, right. So, for mechanical purposes, there is this pulley kind of mechanism that is present. Okay. So, let us consider a cylindrical structure such as that one and a tendon that wraps around it and connects here and then another. So, one is the proximal end and the other is the distal end. Okay. And we are interested in studying forces that are felt or exerted by this tendon. Okay. That is of interest for us. Now, that situation can be modeled similar to a cylinder that on which a belt has been wrapped around or wound around. Let us say that the rope has contact with this cylinder for an angle beta in radians, and this rope or this belt has two tensions, T1 and T2. If there is an external rotation that is applied as shown in this picture, an external rotation capital M that is applied, T2 can be assumed to be greater than T1. For the sake of discussion, let us assume T2 is greater than T1. Okay. In this, small r is the radius of the cylinder, T1 is the tension that is felt on the slack side, or this is the lower tension. T2 is a tension that is felt on the tight side or the higher tension. Okay. All right. Now, let us consider a differential area, a really small area, okay, somewhere in the middle of this contacted area, somewhere I am considering a very small area, okay, that is formed by this sector with angle d theta, where d theta is really small, an infinitesimal quantity. So, we zoom in to this element and what we see is drawn here. So, there is this extremely small sector, that one, that is due to the angle d theta, the radius is r, okay, the radius is r. Now, what would be the length of this element? What would be the length of this element? That would be r d theta, is it not? Well, technically that is actually, let's say it properly. This is going to form the opposite side of the right triangle. So, that would be r sin d theta, but that would be r d theta for small d theta in radians. Okay. So, because of this reason, this is actually r d theta. How did I say this? This is why you have to go back and check the particular videos where we learned how to resolve vectors, right, where we say this is actually r sin d theta, but sin d theta is equal to d theta for small d theta is actually a from high school mathematics. Okay. Sin d theta is d theta for small d theta in radians. All right. A question is, what are the forces on this differential element? What are all the forces on this differential element? Well, on this side of the differential element, the tension, if the tension is some T as shown here, this is T tension. Okay. On the left side, it will be some T plus some dt. Why would that be the case? Why the tension on the left side will be higher? Because T2 is greater than T1. So, as I am moving to the left, the tension will be a tad bit more on the left side, not necessarily a lot more. That will actually be an infinitesimal increase, an extremely small increase in tension. Why would it be extremely small? Because the element size is also extremely small, it is an infinitesimal element. Because of that reason, the increase in tension would also be very small. Now, our interest is to study, assume that an equilibrium has been established and study the nature of this static equilibrium in this element that is of interest for us. Okay. This is our goal. Our goal is to assume that static equilibrium has been established and we are interested in studying this static equilibrium in this small element. Okay. So, we have capital T on the right and we have capital T plus dt on the left. As I mentioned, tension at a angle, let us say, remember that angle has been marked to be theta. So, tension T is the tension at angle theta, T plus dt is the tension at angle theta plus d theta. Okay. That is the tension at that point after d theta. Okay. What would be the normal force? What would be the normal force? The normal force at theta plus d theta. Okay. What would be the normal force? The normal force is the force that is felt here, that is marked in green here, and its value will be some dn. It will be a really small normal force dn, is it not? Because it is an infinitesimal element, so it is going to produce a very small normal force d capital N, dn, okay, a differential force, okay, an infinitesimal, extremely small force. If the normal force is dn, what is the frictional force? Well, for coefficient of friction mu, the frictional force would be mu dn, that is drawn and shown in blue here. Okay. That is the frictional force, which is mu dn. Dn is the normal force, mu dn is the frictional force. Okay. Now, let us call this direction as the t direction and this direction as the n direction. Okay. For historical purposes, this is called as we are using a coordinate system called as the normal tangent coordinate or the NT coordinate system. It does not really matter for this. Okay. That is the n direction and this is the t direction. Okay. I am going to write out the equations of static equilibrium in the t direction and in the n direction. You can do it for x and y also, the results will not be different. Okay. So, equilibrium in the t direction or is in the tangential direction. What would that give us? That would give us, this is the force that we want, but t is acting in this direction, but we want the force in that direction, is it not? Where that angle, what would that angle be? That is actually an interesting question, but you can find out. You can try to use your knowledge of geometry and verify whether this angle is actually d theta by 2. For this angle to be d theta, this angle would be actually d theta by 2 based on our high school geometry. I know this, and this angle would also be d theta by 2. Again, do not ask how do I know, check this is correct. Okay. These two angles on the sides will be d theta by 2. Okay. I am interested in the force in that direction, that is the t direction. That would give me actually t times cos d theta by 2. Is it not? Because that is the adjacent side to that angle, is it not? So, that would be a cos d theta by 2. Okay. What other forces are there in the t direction? In the positive t direction, this is the positive t direction. In the positive t direction, I also have the frictional force, which is mu times dn. Okay. In the negative t direction, I have minus t plus d capital T times cos d theta by 2. Okay. I can expand this t plus dt cos d theta by 2 as t cos d theta by 2 plus mu dn minus t cos d theta by 2 minus dt cos d theta by 2 is equal to 0, or rather these two will get cancelled, t cos d theta by 2 and minus t cos d theta by 2 will get cancelled. So, I will have mu dn minus, or mu dn is equal to dt cos d theta by 2. But for small theta cos d theta by 2 is actually 1. Okay. For small theta, because d theta already is an infinitesimal quantity, here we are talking about d theta by 2, that is almost like cos 0, is it not? D theta by 2 is very close to 0. Because of this reason, cos 0 is 1. Because cos 0 is 1, this will be mu dn is equal to dt, since cos d theta by 2 is approximately 1 for small d theta, is it not? D theta is infinitesimal. Because of this reason, mu dn is equal to dt. Okay. Now, let us discuss equilibrium in the n direction. That is the n direction, is it not? Let us write out all the things that are there in the n direction. What is the force in the positive n direction? That is the reaction force, that is dn, is it not? Dn is in n direction, mu dn is in the t direction. Equilibrium in the n direction gives dn, okay, minus t plus dt times sin d theta by 2, because of this force, is it not? This force or the component of t plus dt in the negative n direction. This is the plus n direction and this is the plus t direction. In the negative n direction, there will be a component of the belt force, right? That component, what would that be? That would be sin d theta by 2 times t plus dt, is it not? That is that component, is it not? That is sin d theta by 2 times, because it is the opposite side. Those who are still confused about how I am doing this, go back to our first few videos where we discuss how to resolve vectors. Okay. So, that would be sin d theta by 2 times t plus dt, but we are not done yet. There is this t force also that comes into the picture, and that would be minus t times sin d theta by 2. Taking the t dt sin d theta by 2 terms to the right side, I am having dn is equal to t sin d theta by 2 plus t sin d theta by 2 plus dt sin d theta by 2. Now, for small d theta in radians, sin d theta is equal to d theta. From high school trigonometry, I know that for small d theta in radians, sin d theta is d theta. So, I am going to use that here. dn is t times sin d theta by 2, let me write this again here, t times sin d theta by 2 would actually be d theta by 2 plus t times sin d theta by 2 would be actually d theta by 2 plus this would be almost 0. Why? Because it is the product of two differentials that would actually, okay, let me write this anyway, that would be dt times d theta by 2. Okay. Now, that is almost 0. Why is that? Because it is the product of two infinitesimal quantities that will be even smaller than those two quantities. dt times d theta by 2 is a very small and extremely small quantity. So, I am neglecting that, the product of second order differentials, I am just neglecting that from the analysis. The sum of t d theta by 2 and t d theta by 2 will give me t d theta. So, that would be Tn is equal to t times d theta. Why am I doing this? Because this is the product of two differentials almost 0, all right. So, dn gives me t times d theta, this is what I get from the n direction, mu dn gives me dt, this is what I get from the t direction. Let me write this in the next slide and continue the discussion. Okay. Mu dn is equal to dt and dn is equal to t times d theta. This is what we have. Now, substitute for dn in the first equation. I am going to call this first equation 1 and 2, sub 2 in 1. What do I get? Mu times t d theta is equal to dt, or dt by t is equal to mu times d theta. Integrate this between the limits of tension and the angles. Okay. What are the two tensions? T1 and T2. What are the angles? 0 and beta. Remember, when we first formulated, the contact area is known to be beta, is it not? That is the contact area. T1 and T2 are the two tensions. I want to integrate this. Integral dt by t between the tensions T1 and T2 is equal to mu times integral 0 to beta d theta. This will give me ln T2 by T1 is equal to mu beta. raised to the power e on both sides. This will actually give me T2 by T1 is e power mu beta, or rather T2 is T1 times e power mu beta. This is a relationship between T2 and T1 that I am interested in understanding. This is called, remember, beta is in radians, beta in radians. This relationship is called as the Euler-Eytelwein formula or the capstan equation. Okay. This is the Euler-Eytelwein formula, Eytelwein formula or the capstan equation. The Euler-Eytelwein formula is T2 T1 e power mu beta, where beta in radians and T2 is greater than T1. Okay. This is the Euler-Eytelwein formula. In biomechanics, this is usually written as the force on the proximal side of the tendon is the force on the distal part of the tendon times e power mu theta, okay, where theta is the angle of contact, mu is the coefficient of friction, Fd is the force at the distal end of the tendon, and Fp is the force at the proximal end. Let me write this out. Fp, force at the proximal end of the tendon. Fd is the force at the distal end of the tendon. Mu is the coefficient of friction. It can be static or dynamic coefficient of friction, static or dynamic. Theta is the angle of contact. Okay. What would be the frictional force? Fr? Fr is the difference between Fp and Fd, is it not? That would be the difference between Fp and Fd. That would be Fd times e power mu theta minus 1, is it not? Or let me rewrite that. That would be Fp minus Fd, which is, substitute the value for Fp, which is Fd e power mu theta minus Fd. That would give me Fd times e power mu theta minus 1. Okay. So, the frictional force Fr is Fd times e power mu theta minus 1. So, the frictional force is a function of the coefficient of friction and the angle of contact, right. That is what we learn from this mini derivation. Okay. Now, a question is, how is this directly relevant in biomechanics? How is this directly relevant in biomechanics? Let us take a simple example, an experiment that was performed in the 1990s, the early 1990s, where they used a similar principle, or essentially the same principle, to find the friction between the flexor digitorum profundus tendon and the A2 pulley. Okay. They took the pulley and the tendon from cadavers, essentially harvested from cadavers, and they applied a known load of 4.9 newtons. 4.9 newtons is applied at 4.9 newtons is applied at one end of the tendon, on the opposite end a linear actuator is resisting this here. This is the linear actuator. This is resisting this force, okay. And there are two force sensors in series with this arrangement, F1 sensor and F2 sensor, okay. That is F1 sensor and this is F2 sensor, okay. And they are making two different angles alpha and beta with the A2 pulley. The tendon, two ends of the tendon are making two angles alpha and beta respectively with the A2 pulley, okay. And what they found was that and they changed alpha and beta. They changed alpha and beta so as to change the contact angle, and they found that the frictional force changed from 0.021 to 0.031, right. And they used this formula to compute the coefficient of friction between the A2 pulley and the tendon, and they found that the coefficient of friction between the A2 pulley and the flexor digitorum profundus tendon is between 0.022 and 0.063. These are really small numbers. Remember that these are well lubricated systems. So, it is not abnormal or it is not entirely unheard of when these kind of small coefficients of friction are presented in the biological system. This is one of the ways in which we could use the previous derivation or previous principles in our understanding of how tendon wraparound causes changes in friction and behavior, right. So, in this video we looked at gliding resistance, tendon wrapping around bone and how that changes quantities in friction, and friction forces in wraparound tendons. Using a small derivation we found the friction forces in wraparound tendons, and friction between flexor digitorum profundus tendon and the A2 pulley, experimental measurement of or experimental estimation of this in using cadaver tendons. With this we come to the end of this video. Thank you very much for your attention.